So, what we want to do now is continue looking at magnetism and talk about a specific example here. So, suppose I have a region of uniform magnetic field into the page, okay? Um, and we don't know what the strength of this field is yet, but for now, let's just call it B. And what if I inject a particle of charge Q, and once again, let's make it positive, into this region? We argued yesterday that the result will be a circle, okay? I should say in the previous video. In the previous video, we argued that this would be a circle, and that means it'll have a radius r. Okay, and because it's now moving in a circular fashion, that means that the resulting force, the electron, or we're assuming this is a proton, but for the moment, just call it a charge. The force that the charge feels is going to be a centripetal force. Okay. And so remember that the centripetal force is given by mv squared over r. Okay. But it's the magnetic force that produces this. So the magnetic force is going to be equal to QVB. Now, we're assuming that everything is at right angles here, right? So if I draw a coordinate system, let's see, X, Y, Z, my coordinate system would look something like this. So X, Y would be into the page, and then Z would be up, okay? So when a positive particle enters the field, it's going to feel an upward force, an upward deflection, and then the angle of the deflection is going to continually change as the direction of the velocity changes, but the velocity will never, the magnitude of the velocity will never change. The direction will, but the magnitude will not. So, as a result, what we can say is when these are at right angles to each other, the magnetic field and the velocity are perpendicular, then what we have is QVB, the magnetic force, is causing the centripetal acceleration, okay? Or really causing the centripetal force. And so from this, there's a number of different ways we can view this equation, but one of the most important would be to solve for the radius. Okay, so I want to solve this equation for the radius, and the speed is the same on both sides, so the v's cancel, and I'm left with mv over r. And then if I solve for r, I get mv over qb. And this is what's known as the cyclotron radius. Okay, so the cyclotron radius is the radius of the circle inscribed by a charged particle when it's traveling in a magnetic field at a perpendicular angle, an initial perpendicular angle. And note that the angles will always stay perpendicular. Every point inside the circle, the instantaneous velocity is still perpendicular to the magnetic field, so that doesn't change, right? Even though the direction of the velocity changes, it changes in a plane that is perpendicular to the magnetic field, so that doesn't change. Now, why is the cyclotron radius important? Okay, well, first things first, note that the numerator is just the momentum. Okay, the numerator is just the momentum, and let me write that out a little bit more clearly. Okay, so the numerator is the momentum, and the denominator is the product of the charge in the field. Okay, and why is this important? So there is a piece of technology, okay, known as a mass spectrometer, and it basically operates on this principle. So if you have a material, particularly gases, and you don't know what the constituent uh, or what the ingredients are of that gas, you can inject it with a known velocity into a magnetic field. And because different atoms in the substance will have different masses, they will all have different circles. They will all have different radii. So the basic way a mass spectrometer works is you've got a narrow slit inside an apparatus, inside a box, essentially. And inside the box, there's a source of uniform magnetic field. And if your components particularly are ionized, then they're going to be charged. And so the charged ions, when they're fired into the apparatus, the positively charged particles, if we're doing this, would deflect to the left. And you can measure this curvature, and the negatively charged particles would deflect to the right. And you could measure that curvature. And that gives you the masses of those particles or ions that make up the substance, and then you can get the individual constituents of your material. So this is a very useful piece of technology, and it all rests on this idea of the cyclotron frequency. Okay. Now, when I have a current carrying wire, okay, let's suppose I have a current carrying wire. Under this circumstance, the individual charges in the wire that are moving will be influenced by any external magnetic fields. And as a result, the entire wire will experience a force from an external magnetic field. And particularly if the wire is embedded in a magnetic field that is perpendicular, then the force will be maximized. Okay, let's see why this works. So once again, if we take a uniform magnetic field and embed a current carrying wire, forgive the wonkiness of my wire. It's sometimes hard to draw straight lines on my tablet. Let's see if we can do a little bit better than that, though. That's better. And so we're going to have individual charges. Now remember, we define current as the flow of positive charge, okay? Even though it is technically the negative electrons that are flowing, we define it to be the flow of positive charge. So if I have a current flowing in this direction, then what I am saying is that I have positive charges that are flowing in that direction. In reality, it's negative charges flowing in the opposite direction, but that means that the effect is still the same. So even when you do the right-hand rule and reverse it for the negative charges, because they're moving in the opposite direction, you still get the same direction for the net force. So what happens is this. These individual charges that are moving, they're all flowing with some velocity, the drift velocity of the electrons. And so you do the right hand rule. In this case, point your middle finger up. I'm sorry, index finger up, middle finger into the screen, and the deflection will then be to the right. So what this means is that if I look at the wire an instant after I turn the current on, it would be deflected something like this. So I look at the same magnetic field and I look at my wire is going to be bowed like this, right? It'll be deflected. And as a result, what we can say then is that the force, we could say, okay, right, F is equal to QVB. For a single charge, when I have lots of charges, I can say F is equal to the sum of all my Q's times V times B, but that assumes I know how many Q's are moving. And it's much easier to do something like this and say, okay, wait a minute, Q times V is the same thing as coulombs times meters per second. But coulombs per second times meters is the same thing. And coulombs times seconds is current. So QV is equal to IL, where L is now a length of the wire. And that would be the meters in the units. And so instead of trying to find all of the forces on all of the individual charges, just look at the bulk current. And we define, and formally, this was QV cross B, right? Formally, it was V cross B. And so in the same way, we say that this is equal to I L cross B. Okay, the current is not a vector, but we can talk about the length of the wire having a direction, and that direction would be in the direction of the current. So if my current is upward in this sense, then L would also be pointing upward. Okay, and it has a magnitude of the length of the wire that's in the magnetic field. So whatever length of your wire is in the magnetic field is L. And if we know the direction of the current, which is the same direction as L, and we cross that into B, that gives us the force on a current carrying wire. So, for example, if we say, let's say we have this kind of circuit where we've got a uniform magnetic field. Let's actually keep it more toward the middle here. We'll see why here in just a minute. Okay. Okay. So suppose we have a region of uniform magnetic field, and we have a wire running straight down the middle, if I can draw a straight line. It's a little bit better. And this wire is connected to a circuit and perhaps a small resistor. Okay. And so if we assume that the wire is a perfect conductor and we have V and we have R, then the current is going to be equal to V over R. And we have the magnetic field of strength B, okay? And we define the direction of current in a situation like this to be the direction of positive charge. And so here's our negative terminal. We've got our positive terminal. Our current is going to flow this way. Okay. So I is going to be downward here, right? And so if I have I downward, then this deflection is going to be to the right. Okay, so this is going to be the direction of the force. And so what that means is, if I just look at the piece of the wire that's embedded in the field, then it would look like this, right? So if it's tacked down here, and if it's tacked down here, so then the rest of the circuit is immobile, then the wire is going to try to bow like this, right, between the two tacks. And the current is not going to be affected. The current's still going to flow, and it's still going to flow at the same magnitude, but it would simply be deflected. Okay. So if we want to do an explicit example here, let's say that we have a magnetic field, and once again, let's just say 0.5 teslas. And by the way, 0.5 teslas is actually a rather large magnetic field. The Earth's magnetic field is on the order of micro Tesla, and compasses still respond to it. At the equator, it's usually somewhere around 50 micro Tesla. At the poles, it's stronger, of course. But near the equator and mid-range latitudes, the magnetic field is usually on the order of about 50 micro Tesla. So 0.5 Tesla is 4 orders of magnitude larger than that. So this is 10,000 times stronger than our Earth's magnetic field. So this kind of magnet would easily do things like pick up a monkey wrench, if as it were. Okay, and so this is a rather strong field. And let's say we've got a current in a wire running through the magnetic field, and it's attached to an external circuit out here, right? So we have a complete circuit, and we've got a current running through here, and let's just give it a nice value of 1 amp, okay? And let's say that the distance, let's choose green. The length of wire that is in the magnetic field, let's say, is 10 centimeters, so 0.1 meters, okay? And the last thing we need to do is define a coordinate system. So let's let upward be y. Let's let x be to the right. And then we would have z into the board. Oh, I'm sorry, z out of the board. So negative z. So with that in mind, B is going to be 0.5 Teslas in the negative k direction. Okay? And our current is going to be 1 amp, and it's going to be in the plus y direction. Now, once again, remember that the current itself is not a vector, but the length that we're going to use is going to be a vector. So this is going to be 0.1 meters in the y hat direction. Okay, same direction that the current is flowing in that region. So this is what we have. And once again, you can either do this where you can say, okay, the force is equal to I times L cross B. And you can say that this is the same thing as I L B sine theta. And when your unit vectors are perpendicular, the sine theta goes to 1, and this just becomes ILB. Or you can use the resultant, or a determinant rather, of the cross product. And in this case, L would be 0.10, and B would be 0, 0, negative 0.5. Okay. And so you can either do the determinant method that we did the other day, or you can do this. And technically, I want this would be equal to I times all of that, right? But so it doesn't matter. And we showed in the previous video that the cross product definitions are equal. So it doesn't matter which one you use. I always say use which one is convenient or the most convenient, especially once you've established the equivalency. And so we'll just use this equation. And this is going to be 1 amp times 0.1 meters times 0.5 Teslas. Okay. And remember that Teslas are newtons per amp times meter. So the units do work out. And we get a force of 0.05. Okay. 0.05 newtons. And while that's not an extremely large force by any stretch of the imagination, it is still strong enough to deflect a thin wire. Okay. It's more than strong enough to deflect a thin wire. And as a result, you would see the wire move. It would try to bend. Okay. And we see this in the laboratory. Now, there's one last thing to note. Okay. There's one last thing to note. And that is this. Right. Pardon me. Remember, we said that magnetic fields were created by moving charges. But when I have a wire and I have charges in motion, These all have the same value Q. In truth, they're electrons, but regardless of how we define them, they have charge, and if the current is moving in a specified direction, then these charges are in motion. And remember, we said that it is charges in motion that create magnetic fields. There are charges in motion that create magnetic fields. So a wire has its own magnetic field. It creates its own magnetic field, right? And in truth, it's this magnetic field that the wire creates interacting with the external magnetic field in the previous example that's responsible for the deflection. You can ultimately derive it from the fact that individual charges experience magnetic field interactions, experience forces from magnetic fields. But it's the creation of the magnetic field due to these charges that creates a deflection force. So do note that these types of materials create their own magnetic fields. And in the process of creating those magnetic fields, they will interact with other magnetic fields, and they will be repulsive or attractive depending on how the fields are oriented with respect to one another. So we will talk more about polarity. Well, you know what? We can talk about it now. So if I consider a typical bar magnet, okay, if I consider a typical bar magnet has magnetic field lines that look effectively something like this. And we consider a north pole and a south pole. And so we define, much like electric fields, the north pole is where the magnetic fields are leaving, and the south pole is where the magnetic fields are entering. Okay. Now, there are a few rules of magnetic fields that I haven't defined yet, so let's actually do those now. And those rules are that B fields will, not with, but will attract, repel other B fields just the same way that electric fields do. Okay. So this is rule number one. The magnetic force can be either attractive or repulsive, just like the electric force. Rule number two, B fields always come in a closed loop. In other words, we will always have a dipole. We will always have a north and a south pole. We've never found a magnetic monopole. We've never found a magnet where we have just a north pole or a south pole. They can theoretically exist, and we have good reasons to think they may have, but we have not observed any yet. And for the moment, we can say that every magnetic field we've ever observed is at least of a dipole form, at least a north pole and a south pole. You can actually have really complicated magnetic fields where you have multiple north poles and multiple south poles, but in general, in a simple magnet, you'll always have a north pole and a south pole. Number three, if I slice a magnet, I get two smaller magnets. So if I were to take a hacksaw and cut an iron bar magnet in half, at the end of the day, what I would get are two smaller magnets and they would each have two new poles, right? And they would each have their own new magnetic field lines. And number 4, north and south attract. Okay, north poles and south poles attract, whereas north pole and north pole repel. And a south pole and a south pole also repel. Okay. North and north repel, south and south repel, but a north and a south will attract. So, what this means is not to jump the gun too much, but if we come back up here, okay, wires will create their own magnetic field, right? Wires will create their own magnetic field. And if I put two wires parallel to one another, depending on how their currents are flowing, if they're flowing in the same direction or if they're flowing in opposite directions, these wires will either bend toward each other or they will bend away from each other. And this is due to the fact of the way the magnetic fields in between the two wires interact. And if you orient the currents in one way, you'll get a north-south attraction. If you orient the currents in the other way, or the other two ways, as it were, you'll either get the north and north repulsion or the south and south repulsion. So, as far as we know, there is no such thing as a magnetic monopole that we have found. Now, once again, not to jump the gun too much, but remember that Gauss's law, when we looked at Gauss's law, right, we had the integral of the electric field over an area was equal to the charge enclosed divided by epsilon naught. And so if I had a Gaussian surface that enclosed a charge, that charge put out an electric field, and that field created a flux through that surface. Okay. Magnetic fields don't do this, right? Magnetic fields, if I have I can't have a monopole, so I have to have something like a bar magnet. And when I have that, if I draw a surface around the magnet, whatever amount of magnetic field leaves goes back in, and leaves and goes back in. So no matter how big or small a surface I have, if my surface encloses that magnet, then I will get zero flux. So there is zero flux for magnetic fields. Okay, so we write this as B dot dA is equal to 0. And this is actually known as Gauss's law for magnetism. And this is actually the second of Maxwell's equations. And Gauss's law was known as the first. So once again, these are the set of equations we're actually setting up to build. So these are the equations we want. All right, so that is hopefully a little bit more about magnetism and some of its the theory behind it and an application to wires. And in the next lesson, we will talk about the source of magnetic fields and talk about the Biot-Savart law. All right, we will see you then.